The topic of today's lecture is hypothesis testing, and we're going to be looking at hypothesis testing from the point of view about making decisions about populations and some parameters describing those populations. An example would be if you have to make a decision whether one process is better than another, or whether to continue production on a particular tool because it's producing widgets that are economically unacceptable. So, their KPIs are outside of desired specs, or there is an unacceptable number of defective components. And these kind of decisions are often based on means of samples, standard deviations of samples, which then lead to inferences drawn about populations. So in reaching those decisions, we always make assumptions which may or may not be true. And a statistical hypothesis is an assumption about the distribution of random variable within a given population. And then we're usually concerning ourselves about with things that we can say about populations. So an example of a hypothesis would be statement that probability that we're going to get number 5 on a fair dice is equal to 1/6. And this is the statement that we can make. So if this is a statement out of which we are starting our consideration of our population, we're going to call this kind of statement the null hypothesis, and it's usually denoted with H0. The null hypothesis is the kind of basis statement that we're going to start, and then 0 indicates that it's a null hypothesis. So if P is just one second, I just need to allow people in. So if P is the probability of throwing a 5, then H0 is, sorry, my series talks to me now. So H0, that P equals to 1/6, probability is equal to 1/6, means that the null hypothesis that the probability of throwing a 5 is 1/6. Kind of straightforward. I said it many, many times, probably too many. Now, we can make many statements that are different than that hypothesis. And all those statements in our consideration are always going to be called an alternative hypothesis. There are many ways of denoting it, HA or H1 or whatever it is. So we can come up with several alternative hypotheses for this situation where we're figuring out whether this dice is fair or not. So for instance, probability of getting a 5 is equal to 1/7. That's one example of an alternative hypothesis. Another example would be probability is less than 1/6, or probability is greater than 1/8, or something like that, or probability does not equal to 1/6. All those statements are alternative statements to our null statement, to our basis statement. And when carrying out hypothesis testing, what we're going to be trying to see is which one of those is correct and which one of those is incorrect, or rather, which statement can we assume to be correct based on the evidence that we have available to us. Your question? Ryan, no. Okay, sorry. Just saw unmuting, so that's why I asked. I'll continue. And the hypothesis may be used when making comparisons. So like in industrial settings, we can compare things like processes. We can compare, let's say, two materials and their strength. So we can say one hypothesis could be that this would be our null hypothesis, that strength of the first material is the same as strength of the second material. That would be null hypothesis for the situation when we're looking at two parameters of two different populations, let's say. Alternative hypothesis in this case comes to mind immediately. The first alternative one that we can come up with would be that the strength of the first material is different than the strength of the second material. Or we could say that strength of the first material is greater than the strength of the second one. Or we could say that the strength of the first one is less than the strength of the second one. So these are all examples of alternative hypotheses. And as I mentioned earlier, a hypothesis is a statement that we make about population parameters based on the evidence that we have at the moment. Now, because the evidence is not complete, we don't have all the information available about the population. When we're making those statements, we're bound to make mistakes. So I'll go to those mistakes in a second. So initial statement, null hypothesis, which difference from initial statement is the alternative hypothesis, and it's possible to compare as well as to focus on specific values. And we can make errors in judgment. So when we look at hypotheses, when we look at our situations here, what we want to see is, do we have enough evidence to reject null hypothesis? Essentially, that's what we're trying to see. We're making some initial statement, and then we're looking at the evidence towards the alternative hypothesis. If there is enough evidence, and we're going to go over what does it mean to have enough evidence. If there is enough evidence from the statistical data that we gathered, we're going to say that we reject null hypotheses and accept alternative hypotheses. If we don't have sufficient evidence based on the sample data that we collected, we're going to say that we fail to reject H0, and that means that we reject alternative hypotheses. So H1. That's kind of a bit unnatural way of thinking about it or stating it, but we reject the null hypothesis and accept alternative, or we fail to reject the null hypothesis and then we have to reject the alternative. So that's what we're going to be doing when talking about hypothesis testing. Now, we're going to make errors, and let's take a look at an example. So, imagine that there is a machine that's producing bolts or some other widget. Those bolts may be made out of some length of metal, and because it's industrial process, some faults may occur. So let's assume that 3 out of every 100 bolts are defective in some or other way. So in this industrial process, we're going to say that the sample that we're going to be using to control our process is of the size of 200. So we're going to draw 200 bolts out of our population to see if our process is running within its parameters, which means that out of 200, we would expect to see 6 faults. Okay. So if a sample of 200 is drawn at random, the manufacturer, the person that we are, the person that's producing those bolts, might be able to make a statement that the defect rate is still 3%, as mentioned here, still 3 out of 100. 1 second. So that still 3 out of 100 bolts are defective, provided that there are 6 or fewer bolts in the 200 bolts in the sample. So we're going to say that in this case, our null hypothesis is that probability of getting a defective bolt is equal to, I'm going to put a colon here, is equal to 0.03. The null hypothesis is that the defect rate is 3%. Okay, so that's our null hypothesis. And let's suppose that we make a decision that if the defect rate raises to, let's say, 5% or more we have to react because we are going to start producing way too many defective bolts. So let's say that our alternative hypothesis, H1, is that I keep putting the equals in here. I apologize. Let me just drop it out and put a colon. Alternative hypothesis in this case, probability is greater or equal to 0.05. Okay, so this is our kind of operating boundary, and let's say that we're going to make the following decisions. If the defect rate is 3%, we can continue production. If the defect rate is equal or greater to 5%, we have to stop the machine and adjust renew parts as necessary, because we are losing too much money. Now, it might seem logical at first, but because you see we're sampling here, we might run into some problem. So let's take a look at sampling a little bit, just to see why are we going to run into a problem. So when drawing a random sample of 200 bolts from this machine with the defect rate of 3%, some samples have to contain no defective bolts. I mean, this is just randomly. Very small number of those samples of 200 will have no defective bolts. Other samples would contain 1. Other samples will contain 10, and so on. We can cover a lot of different combinations of number of defective bolts in the sample of 200. Because we're dealing with a large sample, we can use the binomial distribution to determine the probability of getting some number of those defective bolts. And if you recall, 2 lectures ago, we were talking about calculating probabilities of the binomial distribution. And let's say to calculate probability of getting, let's say, 3 defective bolts would be calculated by 1 minus 0.97 to the power of 200 plus 200 multiplied by 0.97 to the power of 199, the first term, second term, and then multiplied by 0.03, and finally plus 200 by 199 divided by 2 by 0.97 to 198 by 0.03 squared, and so on. So it gets laborious and it's kind of tough calculation. So actually, I'm not going to be using this type of calculation for the binomial distribution. I'm going to use what's called a normal approximation to binomial distribution. So that's what I'm going to do. And in the normal approximation, I can approximate the probabilities using some neat and nifty formulas. So let's just get those out. And I'll talk about the normal distribution a little bit more further on. So if let's say this is the number here, P is equal to 0.03, the alternate probability that part is actually correct, not defective, is going to be Q equal to 0.97. So we can use normal approximation to binomial distribution if product of the number of items in a sample and each of those probabilities P and Q is greater than 5. So that's when we can use the normal approximation. So 200 by 0.03 is equal to 6. So it satisfies the condition of being greater than 5. So that's what I'm going to do. I'm going to use this to approximate the binomial distribution with normal distribution. So when I'm using the normal approximation, I can find some mean of the sample. So X bar will be equal to N times P, the number of items in the sample times probability of getting defective value. So in this case, it will be equal to 200 by 0.03, which will be equal to 6. Standard deviation sigma in this case is equal to square root of NPQ Again, this is a formula for the normal approximation, and it will be equal to 2.41. So now we can use the normal approximation to binomial distribution using this Z value, the standard normal variate. So the standard normal variate for 10 defective bolts. So let's say that we're going to have 10 defective bolts. 10 defective bolts minus mean divided by the standard deviation. Actually, instead of nu, I'm going to put x bar because that's the term I'm using. So now I can calculate the normal variate, 10 minus 6 over sigma. And again, I can put in 2.41 and for sigma. So, which is equal to 1.66. Okay. So now I calculated the normal variate, and I can use to determine the probability of having 10 or more defective bolts. So if I look into the tables, the value of 1.66 corresponds to probability of 95.15%. So that leads to probability equal to 95.15%. So I'll just put a quick normal curve here. Again, normal variate tells me that if I have a normal distribution and some value Z over here, the normal variate, the probability, or like this variate here, means there is 95% of all the values are below this given variate Z. But I'm more interested in values that are greater than Z, so I have to subtract. So this will be 1 minus 0.9515, and that will be equal to 0.0485. Okay, so 0.0485. Okay, so I calculated the standard normal variate, and I found out what's the probability of getting 10 or more defective bolts in the sample of 200. There is a meaning of this. So we have a probability of getting 10 or more in a sample of 200 bolts, even though, and here is the critical thing, even though the defective rate is still 3%. So the probability is still, sorry, the defective rate is still 3%, but we have almost 5% probability of getting 10 or more bolts, defective bolts in our sample, which would lead us to stopping the machine and trying to adjust it. So in this case, we would reject the null hypothesis, even though it should be accepted. And that's what we know as type 1 error. Type 1 error is when a hypothesis has been rejected when it should have been accepted. So I don't have this written out. So type 1 error is the error we should have accepted, null hypothesis that the probability is still equal to 0.03, but based on our evidence, we noted that there are 10 defective bolts in our sample. So we rejected the null hypothesis and accepted the alternative hypothesis. In this particular setup, we're going to make this error 4.85% of times. So that's a problem, I guess. Almost 1 in 20 times we're going to be wrong in saying that we have too many defects. So alternatively, let's assume that our defect rate raised to 5%. So now P is equal to 0.05. And we're expecting that there are going to be 10 bolts. Now, we need to find out how many times we're going to make an error by failing to reject the null hypothesis. So based on the evidence from our sample, we're going to continue thinking that the probability of getting a defect is still less than 5%. So we're going to use normal approximation again. So in this case, P is equal to 0.05, Q has to be equal to 0.95. Number N doesn't change, it's still 200. So the mean for this particular distribution would be equal to 200 times 0.5, that's equal to 10. And standard deviation sigma is equal to, again, square root of NPQ, and that gives me the value of 3.08. So standard normal, the standard normal variate for 9 defective bolts. So
I have questions. Why is 0.5 not 0.05? The mean.
There should be 0.5. Of course, that's a typo here. I apologize, and thank you for pointing it out. So now, the kind of edge case scenario where we have less than 10 bolts is 9 bolts. So we have, again, the sample is defective, there is 5% defects, but let's say that we have 9 defective bolts, so we haven't detected sufficient amount of bolts in our sample. We only picked up 9 rather than 10. So we picked up 9 bolts, but the mean is still 10, and the standard deviation is still 3.08. So the normal variate is equal to minus 0.32. And on the normal curve, that Z value would be located to the left of the mean, and corresponds to the area to the left. So that's Z equal to minus 0.32. And it corresponds to probability of 0.3745. So let me just raise the normal distribution. And the probability is equal to 0.37.45%. Okay. So we have about 37.45 probability that we're going to get 9 or less defective bolts in a sample of 200, even though the defect rate is 5%. So 37, almost 38 out of 100 times, we are going to fail to reject the null hypothesis. We're going to continue production because we haven't produced sufficient evidence to reject the null hypothesis. And we failed to reject it, even though it should be rejected, and that's type 2 error, where hypothesis has been accepted or was failed to reject, even though it should have been. So type 2 error is the case. And in this particular example, we're going to make that error 37% of times. So I suppose thing to recognize is that whenever we're using statistics to make decisions, we should minimize the probability of seeing those errors. So I suppose we should be careful. Now, when testing a hypothesis, the largest value of probability, which acceptable, I guess, for type 1 error, is called the level of significance. So just raise this on. So the largest value of probability is called level of significance of a given test. So level of significance is usually given by the symbol alpha, and it can have values of low values are probably best: 0.1, 0.05, 0.001, and so on. So let's say if you have level of significance equal to 0.05, that means that 5 times out of 100 hypothesis has been rejected when it should have been accepted. And if we look at those different values of levels of significance, then level of if the level is less than 0.01, so your confidence level is 99%, or in other words, only 1 time out of 100 you're going to you're going to reject the hypothesis even though it should be accepted, then you can say that your results are highly significant. Now, values between 0.01 and 0.05 are probably significant, and values greater than 0.05 are probably not significant. So if you ever hear people talking about some statistical or psychological studies results, especially in social sciences, unless they mention their p-values specifically, they're probably talking about p-values of p-values, the confidence level of 5%. And we should really be careful about looking at those studies, because they're more than likely to be incorrect more often than not. Let's go have a quick look at the normal distribution. So as I mentioned earlier, if the number of items in the sample and probability of something occurring, and the complementary probability, so in this case was 0.03 and 90.97. If those values are greater than 5, we can use normal distribution to binomial distribution, and that means that rather than dealing with the binomial distribution calculations, we can use those simple approximations to find our standard normal variates. So then the mean would be equal to n, and p should be capital N here, number of items in the sample times probability of something occurring, and standard deviation is root of product of number of items in the sample and the two probabilities. And that's it. Now, when we're talking about, I suppose significance tests, we need to be familiar with this idea of two-tailed tests. How to tackle this idea, I guess. So let's say that for a set of results, the probably significant result needs to have a confidence level of 95%. So that is equivalent to the hypothesis being rejected when the level of significance is greater than 0.05. And for this, the Z value of the mean will lie between these two values. So we're going to accept the null hypothesis if the Z value lies between -196 and 196. We're going to reject it if the Z value is greater than that, because in that case we have sufficient amount of information, sufficient evidence to reject the null hypothesis. The shaded area is the figure in the figures here, corresponds to the results that are probably significant, and the Z values, again, less than 196 and more than 6, those values are called critical values, and the shaded regions are called critical regions. And we're only going to be rejecting hypotheses on a given significance level if the calculated test statistics lie in the critical regions. So I suppose that's kind of okay. Now, if we have critical regions on both sides of the mean, we have two-tailed tests. Now, two-tailed tests, two tails, because there's tail to the left and tail to the right. Those two-tailed tests are carried out if hypotheses are in the form of H0 P. We have P equals to X, and H alternative P doesn't equal to X. So this is the only case when we would have one-tailed test. Two-tailed tests. Now, obviously, the other two opportunities are if we have one-tailed tests. We can have a tail on the left or on the right. And if we're looking at the right-tailed test, the hypothesis will have a form of H0, that some value equals to something, and then alternative hypotheses will have some value being less than something else. So let's say that we have some test numbers and we're looking at a parameter in the population. So right tail test is looking at values that are greater, which means that left tail tests, the null hypothesis, we're going to have again some value being equal to something else, and alternative hypothesis in this case will be less than some test parameter. And for the levels of significance, these are the Z values of concern. So if we're looking at levels of significance of 0.1, we fail to reject null hypotheses if the Z value is between minus 1.28 and 0.128. We reject if the Z value is less than minus 1.28 or greater than 1.28. For one-tailed test. For one-tailed test at level of significance of 0.01 or 0.005, we're going to fail to reject it, fail to reject null hypotheses if Z value is between minus 2.58 or 2.58. And we're going to fail to reject it if we're going to reject it if it's outside. Two-tailed tests, you can see that those test statistics are slightly higher, and that's again because the probability that value is in the tail has to be split between two tails. So you can see that in this slide, critical region is 2.5 on this side, critical region 2.5 on this side. So on this side, we have 97.5 percent of the area of the normal curve, whereas for a single tail test at the same significance level, this value corresponds to 95%. So that's why we're going to have to use slightly higher Z values for two-tailed tests. Okay, so let's take a look at example and see where this brings us. And for most of those examples, we're going to be using the normal approximation to binomial distribution because we're going to be looking at sample sizes that are sufficiently large. So we have some machine that's producing screws, and it's found over a period of time that 7% of all these screws are defective. Random samples of 80 screws are drawn periodically. So we have some decision rules that are made that production continues until the sample contains more than 7 defective screws. So we have to determine the type 1 error probability and also type 2 error probability if the defect rate has risen to 10%. So looking at the parameters, n in this case is equal to 80, number of items in the sample. Probability of getting a defective sample is equal to 0.07, and probability of getting non-defective screw is equal to 0.93. Both of those products are going to be greater than 5, so we can use normal approximation. So then mean of the normal approximation is equal to product of the number of items in the sample times the probability of getting success, or in this case, a defective sample. So that equals to 80 by 0.07, that gives me 5.6. Standard deviation sigma will be equal to root of NPQ. And in this case, if I sub the values in, I'm going to get that value equal to 2.28. Sorry, not root 28, but actually 2.28. So as I mentioned earlier, type 1 error is the probability of rejecting a hypothesis when it is correct. So type 1 error in this problem is the probability of stopping machine, or in other words, probability of getting more than 7 defective screws, even though the defect rate is still 7%. So in this case, we're going to calculate the Z variate, which is going to be equal to 7 minus 5.6 divided by 2.28, and again, still 7%. So we're going to still get 7 screws, I guess. So until the sample contains more than 7 defective screws. So that's where we're putting into our normal variate. And once I calculate that, I'm going to get that this value is equal to 0.61. And this corresponds to probability of 27%. Sorry, 27. Let me just check. I need to make sure if that's the number. Bear with me for a second. I'll look into my tables. For 0.61, probability is equal to 7291. So looking at my normal distribution, if I get the Z value located over here, that Z value is 0.7, corresponds to probability of 0.7291. That should be probability here, 0.61. And the area under the curve equals to 0.7291. Okay, so the complementary value here is 0.271, let's say. So the defect rate hasn't changed, it's still 7, but we are going to reject the hypothesis because the data that we're getting lies actually in this critical region. So we're going to do it 27% of times. So type 1 error is 27.1, or in other words 0.271%. Then type 2 error is probability of accepting when it should be rejected. And in this case, this probability, in this problem, probability of sample containing fewer than 7 defective screws, even though defect rate has risen to 10%. So parameters changed a little bit. We still have n equal to 80. Our probability changed to 0.1, so complementary probability is 0.9. Calculating mean for this process is x bar equals to n times p, so that's 80 times 0.1, so that's 8, and sigma equals to root of npq, so that equals to 2.68. And last but not least, we have to calculate the variate. So we're getting 7 defective screws, and we're going to get a sample of containing fewer, so 7 or fewer, even though the defect rate has risen to 10%. So let's take a look at exactly that. Z is equal to 7 minus 8 divided by 2.68. And 7 minus 8, 2.68, this value is equal to minus 0.37, and this corresponds to a probability of 0.3577. So now we're looking at our normal curve. We're over here. The Z value we should get in order to avoid type 2 error should be over here, should be in the critical area, but it's not. It's over here. It's in the other area, not in the critical area. We don't have sufficient amount of evidence to reject the null hypothesis, so that's fine. And the probability that we're going to be in the critical area is 1 minus 0.357, so it will be 1 minus 0.3577, and that equals to 0.643. So probability of type 1 error is 27, probability of type 2 error is 64%. So in the next problem, we're going to reduce the sample to 50. going to skip this one, and move to sample means in the interest of time. So for normal distributions, when we're comparing means, if we know standard deviations, we can calculate the standard. I suppose we can we can calculate the standard variate without any issues, and we can apply the correction to the standard deviation that we would have applied in sampling. So it's essentially the same approach as we would do for our sampling calculations for our sample distribution means and sample distribution standard deviations when we're comparing sample means. So I suppose if sample sizes get smaller and smaller and smaller, and again, I think this the values less than 30, we would have to apply the t-test, look at the t-distribution test and get the t-distribution parameters. But for the sample sizes that are greater than 30, we can simply use the normal approximation. But if we don't know the sample standard deviation of the population, we can find the standard deviation of the sample and apply Bessel correction, which is this factor over here. But this factor over here to find the standard deviation. So to find the standard deviation, we simply are going to transpose this formula a little bit. So we're going to get sigma equals to square root of n minus 1 over n multiplied by s. So that would be the Bessel correction to the standard deviation. And again, if the sample size is greater than 30, we don't really need to be concerned too much about applying this Bessel correction, because the approximation is going to be solid. So we can just assume that the sample standard deviation and population standard deviation are the same. But if they're not, we probably shouldn't do that. So in this case, we're going to look at an example where sugar is packed in bags by an automatic machine. The mean mass of the content is 1 kilogram. Random samples of 36 bags are selected throughout the day, and the mean mass of particular sample is found to be 1.03. Now, if the manufacturer is willing to accept the standard deviation of all bags of 0.01 at level of significance of 0.05, if the values are above 0.01, the standard deviation above 0.01, the machine must be stopped and adjustment must be made. So we have to determine as a result of a sample test if the machine should be adjusted. Okay, so let's write out the parameters that we are aware of. We actually know the population mean mu, which is equal to 1. We know sample mean x bar, which is equal to 1.03. And we know standard deviation of the population, which is actually quite handy, 0.01, and also know sample size n equals to 36. So we need to figure out what null hypotheses and the alternative hypotheses for these problems are. So the manufacturer is interested in deviations out of the mean. The mean mass. So we're going to assume that the sample mean, that our null hypothesis in this case will be that sample mean is the same as the population mean, and we don't need to worry about any adjustments. And that leads is the same as, so equals to. That means that the alternative hypothesis has to be, this column has to be that sample mean is not the same as the population mean. If we reject the null hypothesis, if we have sufficient evidence to reject the null hypothesis, we are going to accept the alternative hypothesis, and then we're going to do some adjustments at the significance level of 5%. So the rules, we can specify them. We reject the null hypothesis if the test statistics or the standard normal variate of the sample mean is outside of the range of the standard normal variates corresponding to a level of significance of 0.05. And from the table before, you can remember that. So for two-tailed test is between the range of minus 1.96 and 1.96. So now if the standard normal variate is between minus 1.96 and 1.96, we are going to accept this. So we know the standard deviation of the population. So what we're going to do in this case is the following. So we can calculate the standard normal variate Z and get X bar minus mu and apply the correction sigma, a standard error for the means, sorry, sigma over root n. And that is equal to 1.003 minus 1 divided by root 36, 0.01 over root 36. So that will be 0.03 divided by 0.0016, and that is equal to 1.8. Okay, 1.8. 1.8 is less than 1.96. At the at the 5% significance level for this test, we failed to reject the null hypothesis, and we're not going to adjust the machine. So if I look at my normal curve again, this is our critical values, minus 1.96, 1.96. We did the test statistic, carried out the test statistic. That's all right, nice to do. Now, because the test statistic value is 1.8, which lies in this particular area, it's somewhere over here, 1.8. It's not in the critical area. This is critical area. It's not in the critical area, so our data doesn't carry enough evidence to reject the null hypothesis. We failed to reject it. We and in this case, we're not going to carry out any adjustments. Another example, the mean lifetime of a random sample of 50 similar torch bulbs drawn from batch of 500 bulbs is 72 hours. Now, we're looking at the standard deviation of a sample. So that's an important thing to recognize here. The standard deviation of lifetime of the sample is 10.4 hours. The batch is classed as inferior if the mean lifetime of the batch is less than population mean of 75 hours. Now, determine whether as a result of the sample data, this batch is considered to be inferior at level of significance equal to 0.05 and 0.01. Let's write out the parameters. So for the population, number of items in the population, that equals to 500. Number of items in the sample equals to 50. A mean for the population is 75. Mean for the sample equals to 72, and standard deviation of the sample S is equal to 10.4. Now, we need to figure out what are our null and alternative hypotheses. So in this case, we're going to say that null hypothesis is that the mean is the same as the mean of the population. It's kind of nice starting point. So H0 is that X bar equals to mu. Now, like you see, the fact that X bar equals to 72 should not lead us to any conclusions just yet that this batch is inferior, because we don't know if that data has sufficient amount of evidence at the required level of significance. So like it might indicate at some other level of significance, like less than the one that we require. So we need to carry out our statistical testing before we can say that you know, this batch is inferior at significance level of 0.005. And even, even if data indicates that we should be rejecting the null hypotheses, still 5 times out of 100, we will conduct, we will commit type 1 error, and we will reject null hypotheses even though it shouldn't. Anyway, so rules for this is that we reject H0 if the Z value of the sample is less than the Z value of the sample corresponding to level of significance of 0.05. Now it's less because it's a single tail test, so less than the population mean, and it's we're going to look at I think this side. So if the Z value is less than this critical value, it's in this critical area. So that's Z. It's this critical area. So then we can clearly reject the null hypotheses if we're in this area. Anyway, and we will fail to reject the null hypotheses if our test statistic is not less than the critical value there. So let's carry out some calculations. We know we are given data for the number of items in the sample, number of items in the population, the mean, the sample standard deviation, the mean of the population. And it's a large sample because the number of items in the sample is greater than 30, but we need to apply the sample standard deviation correction. So we need to recognize that sigma in this case is going to be equal to standard deviation of the sample over the root of n. So that's the, and then we add the Bessel correction, np minus n divided by np minus 1. So that's our standard deviation here. If I put this all into my formula for the test statistic Z, we'll get mean of the sample minus mean of the population divided by the standard deviation. Just put sigma and I'll substitute sigma formula in here. So that will be 72 minus 75 divided by 10.4 by root 50 multiplied by 500 minus 50. And all that divided by 500 minus 1. So same as we were using in the sample distributions. And then we have minus 3 divided by 1.471 by 0.9496. And that gives me the Z value of minus 2.15. Okay, so for a single tail test, the critical value for Z is equal to, at 5% level of significance, is equal to minus 1.645 or plus 1.645. Now we're looking at the left tail because we're looking at the value of the mean less than, value of the sample mean less than value of the population mean. So minus 2.15 is less than minus 1.645. So at the level of significance of 0.05, we can say with certainty that we have sufficient evidence to say that the batch is considered to be inferior, and we reject the null hypotheses and we accept the alternative hypothesis that X bar is less than mu. Now, at the level of significance of 0.01 for a single tail, for a single left tail test, the Z value is equal to minus 2.33. Now, in this case, we have to say that the Z value of the sample means lying to the left is not significant. And that's because the Z value of minus 2.15 is greater than minus 2.33. So that tells us that we don't have sufficient evidence to say with level of confidence of 0.01 that this batch is considered to be inferior. And as a result of that, we fail to reject null hypotheses and we reject the alternative hypotheses. So this, for this kind of example, I guess it's probably significant, with some probable significance, we can say that this sample batch has inferior lifetime. Then we're analyzing some mass of carbon in 6 similar specimens of cast iron. Each has a mass of 425 grams. We're getting the following results. So we have to test the hypothesis that the percentage of carbon is 4%, assuming an arbitrary level of significance of 0.2 or 0.1. Let's calculate the values for sample mean, X bar. So we add all of them together, divided by 6 to get 17.22. We can calculate sample standard deviation using the calculator. So enter this into single column table and get the sample standard deviation equal to 0.334. Okay, so we have sample standard deviation. We have sample standard deviation, and we're told that the percentage of carbon is 4%. Okay, so the null hypothesis is that the sample and population means are equal. The alternative hypothesis is that the sample and the population means are not equal, out of 4%, and that's assuming that it's 4% out of this given value. So we're going to reject alternative hypothesis if the z value or t value, if it's a small sample size, is outside of the range for the test statistics corresponding to the level of significance of 0.2 or 0.1 or accepted otherwise. 4% of 425 is equal to 17.0. I think I should have mentioned that earlier, and that's why H0 is X bar equals to mu, and alternative hypothesis H1 is that, again, this should be colon, alternative hypothesis that the mean of the sample is not the same as mean of the population. So we have only 6 tests in this case. We could have taken I suppose we have 6 tests, and because 6 tests is less than 30, we have to use the t distribution. So we're going to have to apply t distribution calculation. So if you remember from the previous to calculate t parameter, we're going to use X bar minus mu, and we're going to multiply it by root of n minus 1 and divide it by sample standard deviation. So for this particular case, 17.22 minus 17 divided by root of 5, so 6 number of items in the sample minus 1, and divide that by 0.334, and that gives us value of t equal to 1.473. So in general, for a two-tailed test like this one, there's a critical region both to the left and to the right of the mean. So for a level of significance of 0.2 or 0.1, the value of a t-distribution lies to the left of the mean, and 0.1 lies to the right. Again, it's kind of symmetrical, the same as for the same as for the normal distribution. Okay, so it's a two-tailed test, and that means that when we're reading out the parameters from the t table, we have to look at the value of t corresponding to 1 minus alpha over 2, because half of the critical region is going to be left of the mean and the other half is going to be right of the mean. And that's how we're going to find out the correct value of the t parameter. Okay, so in this case, we're looking at t values of 0.02 and 0.01. So in this, for the first one, t corresponding to 1 minus 0.2 divided by 2, and that equals to t 0.9, or in other tables t 0.1, depending on how it's written. We have only one parameter that we're looking at, so we're looking at just 5 degrees of freedom. And if we look into the table, the percentile value corresponding to t.09 and the number of degrees of freedom equal to 5 is equal to 1.48, or plus or minus 1.48 for a two-tailed test. And since the t statistic, the value of the t statistics lies between minus 1.48 and plus 1.48, we are going to fail to reject null hypotheses at this level of significance, and we're going to reject the alternative hypotheses, and which suggests to us that the mean mass of the carbon in the sample is the same as the mean mass of the carbon in the population. Now, at the level of significance of 0.01, the value of the test statistics corresponds to t 1 minus 0.1 divided by 2. So that's the same as t 0.95, or in some other tables that would be t 0.05. And again, we have 5 degrees of freedom. And that for 5 degrees of freedom at the 95 or 5% level of significance, we are going to get this value being equal to 2.02. And for a two-tailed test, indicated by using equals or not equals to, we have to add plus or minus. So if the test statistic is between these values, that's fine. If not, then we're going to reject. So again, we're going to fail to reject the null hypothesis at this level of significance, and we're going to reject the alternative hypothesis. So that it is probable that the mass of metal in this particular sample contains 4% carbon levels at levels of significance of 0.2 and 0.1. Now we have to continue on to comparing sample means. And again, we're going to take a lot of samples out of a given population. Say, for instance, 2 light bulbs, like in the previous case. But one sample is produced by one manufacturer, another sample is produced by another manufacturer, and so on. And in this case, we're always going to start to assume that our null hypothesis, that's the starting point, that there is no difference between the means. And if alternative hypothesis in that case will have to be that there is a difference between the means. So if we have 2 samples with means of x1 and x2, those samples have sizes n1 and n2, and those 2 samples are taken out from populations with population means mu1 and mu2 and some standard deviations. Then we can assume that the sampling distribution of differences of the means is a close approximation to normal distribution. So again, we're going to be able to use the standard normal variate, and the standard deviation of the sampling distribution of the differences of the means is given by a formula under square root. So square root of first standard deviation by the sample size plus second standard deviation by the sample size. So standard deviation squared. So then the Z value, the test statistics, turns into this nasty big formula. But we can use it for normal approximation. Now, if the sample size is less than 30, we're going to again use the t value as our approximation for this particular case. So let's take a look at a problem where we have an automatic machine that's producing components, and as a result of many tests, the standard deviation of their size is 0.2. We have 2 samples of 40 components taken, mean of the first sample being 1.51, mean of the second sample being 1.52. we have to determine whether the size has altered appreciably if level of significance is 0.05. So let's write out what we know. We know that the first standard deviation is the same as the second standard deviation, is the same as the standard deviation of the population, which is equal to 0.02. We also that sample size is n1 is the same as n2, which is equal to 40. And we also know that the mean of the first sample equals to 1.51 and mean of the second sample equals to 1.52. And we know that our level of significance equals to 0.05. So we're going to say that null hypothesis in this case is that the size of the component has not altered. So the means are the same essentially at given level of significance, H0, x1 bar equals to x2 bar. And our alternative hypothesis H1 will be that they are not equal. We can simply say that H1 equals to x1 is not the same as x2. Sorry, actually, that's or we can rewrite this slightly differently. If they're the same, then x1 minus x2 equals to 0, or in this case, x1 minus x2 does not equal to 0. And I think that's why we want to write it like that, because we want to use the difference of the means approach in this case. So this is a large sample with known standard deviation. So the Z value is going to be calculated using the standard formula x1 minus x2 divided by this nasty standard deviation, sigma 1 squared over n1, no squares here, plus sigma 2 squared over n2. So subbing the values in, and actually we can simplify this a little bit further because now to do it, I'll actually have x1 bar minus x2 bar divided by root sigma squared plus sigma squared over n. And now I can actually simplify it even a bit further because sigmas are the same as given by the value. So under the this is looking horrible. Sorry, let me erase it and rewrite it. Under the square root, I'm ending up with a really lovely and easy formula is to simplify. So sigma squared over n plus sigma squared over n. Same denominator, same value above the line. So I can simplify it x1 minus x2 divided by sigma squared taken out of the bracket, 2 sigmas in here under the root. So I'll leave the 2 over here. We would have 2 sigma squared, and I'm taking sigma out of the square root so to leave it as without the square, and below the line I'm going to have over n. So now I can put the values in. 1.51 minus 1.52 divided by 0.02 square root of 2 divided by 40, which is minus 2.236. Okay, so if you again look at our null hypotheses, we have equal sign here, so that indicates to me that this is two-tailed test. The level of significance is 0.05. So for level of significance of 0.05 for two-tailed test, the Z value, the critical values are equal to plus or minus 1.96. Plus 1.96. Now, the value of our test statistic is outside of the given range. So what this indicates is that we have sufficient evidence in our sample to reject the null hypothesis and to say that it is probable that the size has altered for those components at level of significance equal to 0.05 or 5%. Okay, so we have those electrical components. So we have two electrical components. The parameters of one, sorry, let me just move this away. How much do we have much left here? We still have a little bit left, that's fine. We have some electrical components there that are compared. The parameters of the first product are, we have sample size of 40, mean value 74, standard deviation 8 ohms. Second product, we have sample size 50, mean value of sample 78, and standard deviation of the whole batch is 7. So we have to determine if there is significant difference between those two products at given levels of significance. Okay, so mean of the batch, mu1, so this is for the first one. Mean of the batch of the second product is mu2. Our null hypothesis will be that the means are the same. So null hypothesis is that mu1 equals to mu2, or in other words, mu1 minus mu2 equals to 0. Alternative hypothesis is obviously that they aren't the same. H1 mu1 is not the same as mu2, so mu1 minus mu2 is not equal to 0. So we know the population standard deviations, sigma 1 equals to 8 and sigma 2 equals to 7. We know sample means x bar, x1 bar equals to 74, x2 bar equals to 78. And we know the sample sizes, n1 equals to 40 and n2 equals to 50. So we have all the quantities that we require to calculate the test statistic for the difference of the means. Z equals to x1 bar minus x2 bar divided by square root of sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. Putting this all together, subbing the values in, we have 74 minus 78 divided by square root of 8 squared by 40 plus 7 squared divided by 50. So that's minus 4 divided by 1.606, and that is minus 2.49. Okay, so for a two-tail test at 0.05 level of significance, where z is plus or minus 1.96, this value is outside of that. So we can say that those two products are not the same. So product 1 is significantly different than product 2 at level of significance of 5%. Again, the 5% means that 5 times out of 100 we would be wrong in making that claim. Now, for a two-tail test with a level of significance of 0.1, z values have to be equal to plus or minus 2.58. Now, minus 2.49 is within this range. So based on our test statistic, we can say that there is no significant difference between product 1 and product 2. So we fail to reject the null hypothesis at the level of significance of 0.01%. Next problem, I think we're almost at the end of this one, 2 more. So we have 2 reaction times for 2 people, and we have to find if there is any significant difference between the reaction times at level of significance of 0.01. So again, for this, we're going to calculate the means and calculate the standard deviations just using the standard formulas. So x bar A is add the values for A divided by 6, so 0.2378. X bar for B, add them all and divide by 6, so that's 0.2345. Calculate the standard deviation of the samples in the same way, as A is 0.00543, as B is equal to 0.00457. So, all right, we have the values that we require. We have some means and we have some standard deviations, and we want to test whether those whether those reaction times are different. So our null null hypotheses will be that they aren't. And I'm just going to say that x bar 1 is the same as x2 bar. So you can rewrite it x1 minus x2 equals to 0. And our alternative hypothesis H1 is that they are not the same. X1 is not the same as X2. Let's transpose to get X1 minus X2, not the same as 0. Now we're using, you can see that this is an equal sign that indicates a two-tailed test. The sample contains less than 30 items, so we have to use a t-distribution. The standard deviation of all the reaction times is not known, so the standard deviation of the population. So we have to apply Bessel correction to estimate the standard deviation of the population. Sigma squared is equal to standard deviation of the sample squared, and then multiply the Bessel correction factor n minus 1. Substituting the values in, we're going to get sigma squared obviously here. So we're going to get that sigma of the approximate standard deviation of the population is equal to 0.00543 multiplied by square root of 6/5, and that equals to 0.00595. We have standard deviation for the population, so now we can find our test statistic for difference of sample means. Again, that's t-distribution. So t test statistic will be equal to difference of the means, x1 minus x2, or in this case xa or xb, divided by standard deviation of the difference of the means, sigma a squared, and sorry, this sigma a in here, right? And in this case, sigma b is 0.00, where is it? Yeah, 501. Sorry. So Na plus sigma b squared divided by b. I can sub the values in to get really nasty simple fraction 0.2378 minus 0.32345 from the means, and then putting in into the standard deviation 0.00595 squared, all that over 6 plus 0.00501, all that squared, all that divided by 6. And we're going to get the value of the t parameter being equal to 1.039. So for a two-tailed test at level of significance 0.01, we have to look at t-distribution corresponding to, depending on what table you're looking at, t95 and t or t.05. We have 10 degrees of freedom because we have 12 items in the samples, 12 items total, and we're looking at two mean parameters. So we have 10 degrees of freedom actually total, not 12 rather, sorry. So looking into the t parameter, the t table, t value for at 0.1 level of significance with 10 degrees of freedom is equal to plus or minus 1.81. And because our test statistic lies within this parameter range, we failed to reject null hypotheses. And we can say that there is no significant difference between these reaction times at level of significance of 0.1. Okay, and last but not least, we have an analyst who carries out 10 analyses of equal masses of substances, which is found to contain a mean of 0.49.2 grams of a metal with standard deviation of 0.41. Trainee operator carries out 12 analyses of equal masses of the same substance with mean of 49.3 with standard deviation of 0.32. So is there any significant difference between the two operators? Okay, so I suppose the the problem here is to find out how to calculate standard deviation for these samples. So we can use the estimate for standard deviation for small samples from the t distribution. So that's given by sigma equal to square root of n1 s1 plus n2 s2, and the standard deviations are squared, and all that is divided by n1 plus n2 minus 2. So again, I'll leave this formula here for a second and just go back to the hypotheses. So my null hypothesis is that the means are the same. The column mu1 equals to mu2. Alternative hypothesis HA is that mu1 is not the same as mu2. So if I put the values in to find the standard deviation here, that's going to be equal to standard deviation for the population, because again this population is carrying out from the same population of the substances. So we're going to look at the population standard deviation. So population standard deviation is square root, put the values in for the first sample size 10, standard deviation of the first sample 0.41 squared, plus second sample size 12, 0.32 squared for the second sample size standard deviation, and all that divided by 10 plus 12 minus 2 to get 0.3814 for the population standard deviation. Again, this is correction factor for the small sample sizes for population standard deviation. Now we can calculate t-value test statistic, difference of the means divided by sigma square root of 1 over n, 1 plus 1 over n2. And that will be equal to 49.20 minus 49.30 divided by 0.3814. 1 over 10 plus 1 over 12, and that's the power of a half. Sorry, I should have written the square root, but just write the power of a half, and that's equal to minus 0.612. Okay, so again, it's a small sample size, so we have to apply the student t distribution at level of significance of 0.5. So we're going to be looking at the t table for levels of significance 0.975 or 0.025, depending on what table it is. Now, the degrees of freedom are given by the number of samples, which is 22 minus two parameters we're looking at. So that's the means. So we have 20 degrees of freedom. U is equal to 20. So for 20 degrees of freedom at this level of significance, t is equal to plus or minus 2.09. Plus or minus 2.09. So since t value based on the sample data is between plus or minus 2.09, we can say that we don't have enough evidence to say that there is significant difference between the results of the two operators at this level of significance. So we failed to reject null hypotheses and we reject the alternative hypothesis. And that concludes the hypothesis testing. I'm going to stop the recording.